Okay. Hello. Today I wanted. Well, this will be the last meeting of this quarter, and I will continue with the private information retrieval. Show also a variant of it, PIR right, and possibly we'll get to ORAM also. I'm not sure if we'll get there, but at least we'll signal the more general form of these things, and I want to focus on a tool that I find very beautiful. It's something called distributed point function of Gilboa and Ishai. Okay, so it's a beautiful tool. It's relatively new and it has applications to all these domains and more. Okay. Yes, and you will see that it has some, also similarities to this recursive solutions we have seen for PIR. Okay, like recursive. Okay, well, it's a square root solution we saw for PIR. Okay. So first of all, what's a point function? Before we start with a distributed point function, so a point function is defined by an element in the domain and an element in the range. So, but it's a function from bit strings of length x to bit strings of length y, such that the point function indexed by this xy pair, when I evaluate it on any point in the domain, I get either value y, but that's only on one argument, if x prime is equal to this argument x here. But for all other arguments, I get a 0 in this range. So it's a point function because it's 0 everywhere except this one point, right, on which the value is y. Okay. Okay. So what's the distributed point function? It's a pair of algorithms generate and evaluate, such that, and I'll give it here in a 2-server version of this notion, where you generate a point function on inputs x and y, which define a point function, but you generate two you know what, I'm going to call it keys. Okay, K1 and K2, such that for every element in the domain, if one party evaluates, runs the evaluation algorithm on this key and applies it to argument K prime, X prime, think of it as a PRF. This is a PRF key, and this is an argument. And the other party, so if, let's say this is, I'm going to call this A1, and the other party evaluates this evaluation function using key K2, on the same argument x prime, then if somebody XORs the two PRF computations on these two PRF keys, K1 and K2, then this reconstructs the point function value defined by this input-output pair at x prime. Okay, so the point function is, as far from a pseudorandom function as you can get. It's zero everywhere, and some value y at one point. And there is a way to encode this input-output pair into two keys, such that an individual who gets K1 can evaluate this function, individual who gets K2 can evaluate that one, and the XOR of the result encodes the output. Okay, so now, with the following secrecy requirement, that Q1 hides the XY pair in the sense of semantic security. Okay, so in other words, K1 is like an encryption of XY. So it's a standard notion of semantic security where you say for any two XY pairs, X1, Y1, and X2, Y2, if you compare two processes, one that generates K1 using the generate function on X1, Y1, and the other generates this key on input X2, Y2, then no efficient attacker can distinguish between K1 generated in one way versus K1 generated in another. Okay, so it's exactly the same notion as encryption, and same for K2, right? So both these keys individually hide input XY. Now, together they don't, because just by the correctness properties, somebody who gets K1, K2 can just evaluate it on all elements in the domain and learn XY that way. Okay, so that's not an efficient procedure, right? Like you would have to evaluate everywhere, but clearly you learn information about XY. If you just evaluate these functions on some input, you learn whether these inputs are equal to X or not. Okay, so you leak information. So maybe one what the correctness imply is that for every X prime not equal to X, the fact that this is A1, A2, XOR to this value, well, this value is a 0 for all those arguments, which means that A1 is equal to A2. So in other words, eval of at X prime using K1 is the same as eval using K2 of X prime. But for X prime equal X, is the 2 XOR to Y. Right? Because at this argument, the two values returned by these evaluations XOR to y. So if K1 is supposed to hide this this point, then somehow if I only have K1 and I evaluate this function on different arguments, and you have K2 and you evaluate this function on let's say the same arguments, then the values that we get must not tell us. So individually, I evaluate this function and I cannot tell where this point is. But the two keys have the property that that these values are going to be the same everywhere, except of one spot where they differ, where they XOR to y, and otherwise, you know, it's they're same everywhere. Right? At x. Right? So if you think of these as pseudorandom functions, okay, so these are keys to a pseudorandom function. I evaluate, I get some values that look, although this is not, so a function is not pseudorandom to a person who holds the key. And yet, so this is not exactly like a standard notion of pseudorandom, right? But the key K1 must have the property that when I evaluate, I get some stuff, and none of the stuff tells me, did I evaluate on the right X, where this hidden argument X? So this is rather perplexing property. How can you have a split? You know, how can you have two correlated pseudorandom functions where evaluator holding the key will come up, these two functions are synchronized. They output the same values everywhere except at one position. Okay? So somehow this key must encode that one position and differ on that one, but it is not, the key itself does not reveal where the position is. Okay, so it's rather surprising that this is possible, right? Like I think that if you view this, you know, how can you construct such a tool? So let's see how to use this. Okay, so let's motivate this by use. So so a distributed function gives you an immediate PIR, private information retrieval, but to server private information retrieval. So what's a PIR? The client has an argument, and it's a two-server PIR. So there's two servers who have a copy of an array. The array has an element, and X is an index into the array. And the client will use a DP, you will generate a distributed point function instance encoding the argument X and the value 1. This will create two keys. And what these guys will do, that they will send the responses computed like this. They evaluate this function So S1 evaluates using key K1 at every point in the from 1 to n, and so because the domain is the range is it's a bit, so this is a function that returns bits, right? The length of this is a single bit string, so this will be bits. So this bit is either 0 or 1, and I multiply this bit by location at the ith location of the array, and S2 will send Z2 computed in the same way, right? But using key K2. Okay, and it's easy to see that if the client computes just XORs the two, then this is an XOR for all I of evaluation of this function at I using both keys. A product with an ith element in the array, right, by the linearity of XOR. But this, by the distributed function property, is equal to 0 for all I not equal to X, and 1 only if I equal X. So in other words, this bit is the same as this bit for all entries I not equal to X. Therefore, in the grand XOR of everything, the corresponding ith item at A is going to XOR out. The only place where this and that differ is position X. So because they are bits, so one of them is a 0, the other is a 1, or vice versa, right? So therefore, that entry is going to enter into the equation, and that will be the only entry that is not crossed out. So this would be equal to AX. Okay. There is also and look. Well, okay. So what is the what's the bandwidth of this? Zi and Z2 is just the payload of A elements, right? So so this is the minimal bandwidth. On the way back, the value that is returned is as big as an entry in the array that is being retrieved. So that's a minimum bandwidth, right? Okay, times 2, but that's okay. So so the bandwidth is, but you also add the length of these two keys. So well, it depends on the DPF. How big are these keys, right? So let's see. So these are DPF keys. But okay, cutting, shortcutting the story. They are log n sized. Okay. Okay, so mystery reveal. Okay, but so that's the solution of OI Shy 14, and so far it hasn't surpassed. So this is way better than what we have seen before, because so Tuesday, the basic solution was square root of n with much. So for both the computational and information theoretic. For computational PIR, using more sophisticated encryption, we can drive down the size of the keys to polylog factors. But the cost on the server grows, because for every entry you have to do a computation that is related to that encryption. The more complex the encryption, the more complex that operations. Here, it is as inexpensive as the information theoretical PIR, right? It's an XOR, except, of course, okay, so no, you also have to evaluate these functions at every point in the domain. But the beautiful thing about the solution is that this will use symmetric crypto only. So it is orders of magnitude, faster than stuff using public key crypto systems. Okay, so is it information theoretic PIR or is it computational? It's computational. These keys are effectively an encryption of these arguments. So it's up. It will only with computational security they will not reveal to these parties. And at the same time, there's a two-server PIR. So once they get together, they can reconstruct, right? So you pay the price but in terms of security properties, right? But it is in some sense, in practice, in the end, you don't care whether it's information theoretical or computational. I mean, as far as like final application goes, like the tools, they might, indeed behave very differently. And we love information theoretic stuff because it makes it, it is the easiest to use. Okay. Another thing you can do is now you can also have private information right. Okay. So what is the private information right? The client has a location and a value, and the servers have a distributed way of keeping the array. But now, well, if they knew the array in the clear, then what's the point of a write? To write a value v into the location at array, into the X location of the array. If these guys knew the array, then there would be no secrecy properties, right? Because they would see where a new value was written. So the write makes sense only if the array is somehow secret from these guys. So let's think of this as a secret sharing of the array. Okay, and take an XOR sharing. And I want a protocol such that these will be changed to AI prime, A2 prime, such that the new sharing shares a modified array, which is like A, so which is equal to A everywhere, except that A prime of at position X is equal to this new value V. Okay, so the new array is the same as the previous one, except that it has V written at position X. Okay. Okay, so how can I do it with the DPF? So actually, I have to need the PIR read to get the value, the old value of this at position X of this array. So so this is okay. It's not going to be a pure solution. It's somehow a solution that requires the presence of the standard PIR. And but okay, but that aside, if you had a PIR that allows you to read the previous position, then the client would do a DPF at using encoding position X into these functions, and the value would be delta, where delta is the old value of the array XOR the new value. Okay, and this generates two keys. And the way that the servers will take these keys is to do the following. For every I, A1 prime at I is the A1 at I XOR the eval using keyword 1 at I. And A2 does the same. So for every I, it sets A2 prime at I to be A2 at I XOR eval K2 at I. Okay, and now see that for every I, if I XOR these new memory value, right? So this is a value of the new memory at point I, right? Because the secret sharing is just XOR sharing. Every element is an XOR of the element of A1 and an element of A2. Okay, so this is equal to the XOR of the previous, right? So the XOR of this with an XOR of that, and that is the old array A item. XOR these differences, right? But the differences by the DPF properties. So this is eval at K1 at I XOR eval K2 at I, and this is 0 for all I not X, and delta if I is X. So therefore, it is exactly that's what I wanted. So therefore, the value of the new array is the previous one for all indexes except at X, where it's equal to AX XOR delta, but I set it delta in this way, and then now you see why I needed the previous value of the array at point X, because this will be equal to V, and so that's if I is X. Okay. So maybe this is a decent segue to so we have a way to read, and we have a way to write, but the write depends on the read, So this is really not a full write. So if I have one place from which I read and the other into which I write, then if that's my mode, right, where I have to read the previous value, then clearly I can only write to new locations. Because if I wrote to one location twice, I would make a mistake, because read is from a stable database. I cannot write into it. These are two different data structures. This one, I need the same values on both sides. And this one, I need XOR sharing of the array. So the same data structure does not support both read and write. So this is not exactly right. So it's a write with a bunch of asterisks. But I can use the two to implement essentially general purpose read and write memory. So here is an oblivious RAM problem, ORAM. So this started with the work of Goldreich Ostrowski and had many. It's a beautiful problem with lots of practical applications to privacy-preserving storage and computation on large data. So it's a generalization of private information retrieval in a way. The client, here is the server or a whole group of servers that have some representation of a memory, okay? And think of it as encrypted memory or secret shared memory if you are in a multi-server setting. And if it's encrypted, then, well, it's encrypted under some key, the client has the key. And then the client, when he wants to read, there is a read operation where they perform some protocol on this encrypted or secret shared memory and client's location, where the client retrieves the plain text value of the memories at that index, and the servers perhaps they get re-encryption or re-sharing of the array, but no info on X, right? Okay, and also you can have a write. So the servers performed some operations such that at the end this corresponds to a modified memory, which is equal to the previous, except W at position, except this new value V at position X. Okay, and here we sort of don't care what the client gets from this. And the two operations are, you can combine them in any order and keep on going, reading and writing, and this is consistent, and it has the expected secrecy properties, right? So the memory is not leaked, entries of memories are not leaked, but also positions of read and positions of write. And why not also make the read and write protocol indistinguishable to the servers, right? so they cannot tell like were you reading or were you writing. How is it different from PIR? Okay, so so as in PIR, private information retrieval, we want sublinear bandwidth, right? Because the trivial solution, this is encrypted memory. It's just sent over to this guy. He reads and writes and re-encrypts it back. Okay, but that has a linear bandwidth. And as in PIR, positions read, write, location hidden. Okay, but what's new here is, well, of course, the fact that you can do both, read and write, right? So first of all, it's the fact that you are writing and reading, but also a memory A is hidden from the server or the servers. And this is not a PIR thing, right? Like, so in PIR, the memory, it was not understood to be the property of the client. It was some service that client used, and it was that service's data. So the data was known to the servers. The location of retrieval was not. Here, it's an outsourced private memory, where the memory is encrypted under a key. Now, PIR, you can, in a sense, like immediately upgrade it to this property. Just make the memory that servers store encrypted under client's key. So they know ciphertext, right? So they use the same stuff of PIR, except that their data is ciphertext. And so client retrieves these ciphertext and then locally decrypts them. Okay, so that's kind of not a problem for PIR. It's the reading and writing that is not obvious. And what you get here is the sort of an inkling for how you could do it. Because if you can read and you can write, perhaps you can have a cache where there is intermediary information, right? Like where think of so there is many ORAM solutions. All of them are recursive, I think. Okay, these are the ones I know. And here is one way that you could do it with recursion using these tools. So you have a way to read and you have a way to write. The only problem is that the two data structures are different, right? And also you have an inconsistent write if you have rewrote the same location at the same location. Okay, so add to yourself a cache. If let's say I will only do some fixed number of reads and writes. The cache has to be a size of that fixed number. Okay, and let the cache be a general purpose memory. It's a general purpose ORAM. So now imagine that you have PIR implemented this way and a PIR write implemented this way, and then you have a smaller general purpose ORAM implementing a cache. And you read this following way: you read from the PIR main memory, and you read from the cache. If there is a value at the cache, you take that one. If there is no value at the cache, then you take the one from the main memory. Okay. Now, how do you write? You read as before, so from the main memory and the cache, and compare, right? And you always, the cache takes priority. Then you write using this mechanism, and you write also to the cache, which is the general purpose memory. And okay, that's it. Except, so that works, right? But okay, what's the problem? First, what if you read more than the size of this cache? Then you refresh. In other words, you upload the whole cache to you, and you regenerate both the read and the write. Yes, okay. You know what? No. So the write contains the new memory, right? The cache was only used to make write consistent for this operation, right? The write memory has the correct new memory. So you kill the cache, delete the cache, delete the write memory, the read memory, and retrieve the write memory and repopulate everything using this what you retrieve from the write memory. Now, okay, so after, let's say k, let's say size of cache is k. After k accesses, you pay the linear cost of n. But that will amortize, because if, let's say, you set k to be square root of n, so you pay linear cost every square root of accesses, so the amortized cost is n over square root of n, square root of n. Okay, and you can actually make it better, make the cache larger, make the cache n divided by some constant factor. Then how often do you do this refresh? N over this constant factor, and it costs you n, so the amortized cost is that constant factor. Okay, and how do you get the oblivious, so how do you implement cache? Recursion. It's the same exact solution, but for a smaller memory, and that's all. Now you have an ORAM, right? You have a recursive ORAM from read, write, and a cache, and then eventual refresh after the cache fills up. Okay. Okay, so now now let's try to actually explain how the DPFs work. Right? Okay, so how is the Galois-Shy DPF construction? Well, so here is the start. You can implement a DPF in a trivial way if the first key is n random values, and K2 is also n random values, which secret share the following vector: y times e I. EI is the vector, is the indicator vector. So it's 0 everywhere except of 1 at the ith position. So this is at position I, at ith position. So I have a change of notation. The DPF will take input I and Y. So this is the position, the secret position. I denoted it X on the previous slides. Now I'm denoting it I. So this product vector, right? It's zeros everywhere, except of single place where it's Y, and that position is at position I, right? So in other words, K1 and K2 are just a secret sharing of this vector. So these are fully random, and these are all the same, except at ith position, where these XOR to Y at ith position. Okay, and send these keys to the two players, and the eval at key K and place X is just the X place in the key, right? So recall that that's what we wanted of the GPS, that the two keys somehow encode random functions which are correlated. They are whose values are equal everywhere except this one position. And the evaluator doesn't know which of these positions, where is this secret position that is correlated with the other key. Well, that's exactly what you achieved here, right? This is just explicitly a random vector, and so is this one by properties of one-time pad. This one is also a random vector individually, right? And so just retrieval of the position of this position of the values at the position gives you exactly this property, right? So so this is what the what each player would do, and you get the property that we wanted. So it's immediate, right? Except that so this works beautifully, except for the fact that these keys are as long as the whole array. Okay, so but we can use the two-dimensional trick that we showed in the PIR solutions. So think of the point function as encoding the location as in a two-dimensional array. So now think of A as an array that is indexed by a pair ij, and both of them are only square root of n size, right? So the range here is square root of n. Okay. So now I think of my location as a pair, and a value, well, as before. And so now the point function is on the domain is pairs, okay, and the values are as before bit strings of the length of this argument. Okay, so how did this help? Okay, let's use the two-dimensional, exactly the two-dimensional solutions that were the basis of both computational and the basic solution for computational and information theoretics to server PIR. So if I generate using this secret location, and my secret location I will denote I star J star. And what I generate is two keys, K1, K2, where K1 is square root of seeds. And K2 is square root of seeds, and they are the same seeds, except of one position where they will differ, and it's a position of okay, and sorry, I will keep on using this notation where I will be the column, and yes, and J will be the row, where the I star seed in key K1 and the I star seed in key K2 will differ. So seeds differ only at position I star. And I will use these as seeds. So I will need a pseudorandom generator, PRG, onto which takes a seed and creates square root of n. So if seeds are identified with columns, I will regenerate the whole column of basically this kind of. So this solution chunks them up into square root blocks and condenses them to seeds from which the square root block of this is going to be regenerated. Okay, that's the whole idea. So square root n times the length of y bits. Okay, so it's a PRG that generates this many bits given a seed. And now, how do I use these keys? So eval using this any key like this. So a key is a string of seeds. It's either that string or this string. And when he evaluates on a position ij, so that encodes. Yeah. So okay. Well, we move to a two-dimensional indexing, right? So this is the index at which the evaluator evaluates this function. And this is the secret index, right, that encodes point y of the point function. So how does he evaluate? He runs the PRG on a seed, the ith seed in this, regenerates this column, this chunk of seeds, and takes the one corresponding to location J. Okay. Well, okay. So what did we accomplish? Now note, if I look at the, so let's say this is the evaluation. So if I look at the evaluation of the first server having K1, and I XOR it with the evaluation of the second server at the same location, then, okay, well, what are these values? It's G at Si at S at J XOR G at Si at J, which is of course equal to 0. And when is this happening? Where for all I not equal to I star, right? Because the two keys have the same seeds at all these locations. So both the first server and the second server will generate these values in exactly the same way. Okay, so far so good. And what about for I star? Well, then this will be Si star 0 at jth location, and G of Si star 1 at jth location. Well, is it Y? Well, no. We didn't even use Y creating these things. So this is not 0 if I is I star. Okay, so we didn't yet encode a Y into this XOR. But here's how we can do so. So add a correction vectors. I will call them correction words 0 and correction words 1. So how long are these correction words? As long as the columns of a length square root n y bits. And the corrections, so each player will use his key to evaluate this. And then we'll use a chunk of the correction vectors. So the correction vectors are columns. And so it will use him at position J. And the correction vectors have to have the property that I will use them in an XOR shift. So the server will evaluate G on a seed that corresponds to that column, look up the J's position, and then they look up the J's position in the correction vectors and use them as XOR shifts. Now, the correction vectors have to have the property that when I use them in here, they will not change this outcome. In other words, that will only be possible if S1 and S2, the two servers, use the same correction words for the the same entry of CW0 and CW1. Think of CW0 and CW1 as a random vector, and the key, if S1 and S2 use to shift their values using the same of these two, so either J's position in here or J's position in here, but in a synchronized way, so always the same, then, well, they shift each of these by the J's word in here or a J's word in here, but if they do the same one, then it will cancel out and it will be still here. If we manage to somehow encode that the only position where the two guys, one of them is going to use the J's position at CW0, and the other will use the J's position at CW1, then only in this case, then these results will be XOR out by the XOR between CW0 and CW1. So let's make CW0, CW1 an XOR sharing of this vector, okay, of this shift vector. Okay, not exactly, of y times ei. So this is the shift vector, 0 y everywhere, everywhere except 1 y, right? But we also have to cancel out this stuff. So we want to cancel out S1, sorry, that was a typo, I star 0, and G applied to Si star 1. Now, if these correction vectors are a random XOR sharing of this vector, then, and if S1 uses jth entry in here and S1 uses jth entry in here, then these values, so the effect will be, so if for all I that are different than the target place I star, S1 and S2 shift their eval k by same, by either by CWB at J for same B. Then this property will be preserved. So this is our goal. We want them to use the same vector of the same of these two at all positions that are not I star, and for I equal I star, let's say C1 uses CW0 at J, and C2 uses CW1 at J. Well, in that case, now eval K1 at IJ XOR XOR eval K2 at IJ will be these functions, right? So G Si J XOR G Si J XOR CWB J XOR CWB J, because both of these, if I is not I star, so by the first property, if both of them took the same CWB, right, then the first guy's contribution is this, the second guy's contribution is that, and they are XOR out to 0. And now, if at this location, S1 uses this to shift and S2 uses this to shift, then the output will be G for I equal I star. It will be G S I star 0 at J's position, XOR G S I star 1 at J's position, XOR the secret sharing, right? CWB, CW0, XOR CW1. But this is this vector. So, okay, so by this property, this whole thing equals YEI at J's position. No, sorry. Okay, mistake. Here, this should be J. I just copied it from the previous, right? So where I had a just a one-dimensional representation. So here, I will use EJ, right? Because I want to encode Y into the J's position in this column. So this is the indicator vector, right? So at J's column. So this whole thing is this vector at J's position, which is Y. Okay. Did I lose you?
I'm not sure why are they showing the case where I is not I star?
Are you asking how can we accomplish this, or why is it important to accomplish this?
Why is it
so far I only explained why that would be good, not how to achieve it.
No, but I meant the first one, the one. Why do we need that?
The point is that they have to, the way they evaluate has to be uniform, right? They don't know what is I and what is I star and what is J star. So at every index, they take the seed corresponding to that index, do a PRG on it, look up J's location, and then apply these correction vectors. Again, this must be somehow uniform. And the way of the, we need the correction vectors to be this way to somehow go from this messy property of being non-zero to the clean property of being Y at position J, right?
Oh, okay. So we are giving them the correction vectors for every J. Oh.
Yes, the correction vector is as long as the, it's as long as the is this many entries, right? It's the square root of entries. They correspond to a whole column.
So I guess my question is how do they choose the same B in the first case, and they choose different. In the first case, when I is not I star, they choose the same B.
Yes, right. So by same bit B, yes, right. And so we still have to get this type of synchrony, that there is square root of rows, and columns, and for each column that is different from I star, S1 and S2 must be told to get the use CW. Both of them are told either use CW0 or use CW1, but they're told to use the same one. And the only place where they're told to use a different one is the I star location. But this is trivial to achieve. Just amend K1 and K2 by vectors of square root of n bits, T1 and T2, such that T1 and T2 are secret sharing of the EI vector. In other words, T1 is random square root of n long string. Sorry. And T2 is T1 XOR EI. In other words, it's no T1. It's T1 XOR 0, 0, 1. Well, this is at I. Sorry, and I star at I star position. So how can they know to use? And so the way they these vectors tell them this is a vector of square root of n bits, 1 bit for every column. And so okay, so here's the final evaluation. Eval using k and this vector t and the vector CW0 and the vector CW1. Okay, so this is the new key at point ij is I look up the okay. So sorry. So this is a vector of seeds. Yeah. Okay. Sorry. This is key k, which was a vector of seed. Okay. I look up the ith seed in this vector and evaluate the PRG on it. Then I look at I take the jth block. That's as before. But now I use a correction. I use a correction vector. Which one? The one that is told to me by the ith bit in here. And that's it. Because these bits are formed so that at every position except of I star, the bits of here and the bits of there are the same because right. The only place where T1 and T2 differ is I star. Otherwise, there are random bits, but they're the same bits. So S1 will take the same CW element, CW vector, as S2. And both of them take the jth chunk of this correction vector. So in other words, right, so they take the two, right, they use the same correction vector, and that is assured by the fact that ith bit in these is, okay, sorry. So now I use the same index. Okay. Okay, sorry. T1 and T2 are indexed. Yes, sorry. These are the.
Okay, so.
Okay, so let's rewrite. I take CW and I look up the T. This is a vector. It's either T1 or T2. And this is a vector. It's either K1 or K2. And I use T at ith position in this vector, and then I do that at yeah.
I'm not sure I understand. I think before it was correct.
Yeah, so the problem is that I use two ways of, I use the subscript at t for two purposes. To distinguish between the vector t given to the first server and the second server. And here I use them, okay, yeah, so this is, yeah, okay, so let's use w at position ti, and then I take the jth element in that.
Okay, so both CWs are being given to both parties. So
you know what? Let me do the same indirection here. So let's call these bits b1 b square root of n. So t is a sequence of bits. T1 is some sequence of bits like this, and T2 is some sequence of bits like this, where the T1 and T2 are the same sequences, except at position I star. So using this notation, this is the I bit. Okay, so now I don't have this double usage of this T subscript. Okay, so okay. So now I got I get this property, right? Because so no matter what place I evaluate, if I XOR these two values, the one that S1 generates and the one that S2 generates, I get this and that, depending of whether I'm at different from I star, whether these are the same, or I'm at I star, whether these are different. And then I also have contribution from these corrections. And if I is not equal to I star, these bits in T1 and these bits in T2 are the same, right, by this property. So therefore, it's some B, okay? So this B is the ith bit in T1 and T2, but at I different from I star, these two bits are different, are the same. Sorry, these two bits will be the same, right? And these two bits are the I star bits in respectively T1 and T2, which they're either 0, 1 or 1, 0, but it doesn't matter, they're different. So therefore, one of these guys will contribute this value and the other will contribute this value. Okay.
Okay, I get it now. It's just that when you wrote the second goal, it should be then that S1 uses CWB, and in the second above, there, yeah, it uses CWB, and S2 uses CW1 minus B.
Yes. Okay. Good.
That was making me confused.
Yes. Right. So. So otherwise, you know, S1 will know that, well, it's always at exactly. So this is yes. These two bits they can be 0, 1 or 1, 0. Yeah. Okay. So what did we gain? Okay, so far we have a square root solution, right? So the cost is what's the size of these keys? It's the square root security parameter. So these are seeds S1 to square root of n plus where these are the CWs. No, these are the T. The T vector of bits plus these, which are square root of n times the length of y. Right. So okay, square root of n. How to get order of log from this and its recursion. So I am clearly running out of time, but let me just draft how you would make it recursively really quick. Okay, hold on. So think that K is really the S1, B1, S2, B2, S square root and B square root of n, right? So the keys and these indicator vectors, the seed and the indicator vector are really combined. So this is a secret sharing. So this is random, okay, and x1 and x2 are the same, except position I star, where S I star, where the XOR is some random value, because in fact you don't care what's the at this one position these two seeds differ. You don't exactly care how they differ. And bit 1, so this is the Si star 0 XOR Si star 1, and this is the T bit at position I star. Okay, has to be 1, the difference between the bits. Okay. So in the basic thing, I gave you these two players S1 had key K1 and key K2, which were square root of n long, and they allowed me to evaluate the DPF function on basically square root n long, column dimension. And if the keys have to have these properties, they're the same everywhere except of this one location, where they encode to a fixed value. In fact, the first part we don't care, but the second we care. Use recursion for that. Use recursion recursively recreate this case using the same solution, but now to apply to the case, right? Because what is the DPF? It's some way of creating functions which create two vectors which are identical, which look random, except that there's a target location where they differ by a target XOR. Well, that's exactly what the key 1 of S1 is, and key 2 of S2 needs to be. They need to be two random vectors which at some secret location I star differ by a fixed amount. Okay, sorry. Yes. So how do I, in the basic solution, in the square root solution, in the square root solution, in the square root solution, I just these two keys were simply sent over, right? So the generator created these square root of length random keys and sent them to S1 and S2. But generation of this can be thought of as an instance of a DPF. So now apply the previous solutions recursively to that square root vector. Okay, in other words, have the domain I you represented as a fourth root by fourth root, right? Where there is this one location I star, which is really now a pair, right? Which is exactly the solution we had, but the final outcome is not, it's not an Y. It's the key. It's what you will output from this is the keys that now you recursively use in here. Okay. Now you need also these correction vectors at recursion. So if you form the recursion that way, then your final recursion vectors are square root n size. So so this is the final level from square root of n to n. Your these things have length square root of n, and the level before is from the fourth to the second, right? And at this level, the CWs have the size like this, okay? And okay, so eventually you start with, you stop at some place, right, where this it's a small initialization where you just simply give these keys, okay? But this is whatever root of n you're happy with, and then the solution works recursively. And but unfortunately, the only things that you have to get are these CW vectors at each point, right? Because that is necessary. So we have kidnapped both of these, and treated them as a single key. And instead of transferring the square root of n size of material, we apply the solution recursively to regenerate these entries locally. But we still have the CW, right? And the CWs we cannot condense. Okay, so the recursion didn't quite work yet. Well, change the dimensions of these things. So rather than make it square root by square root, sorry, let's flip. Make it n over some constant and constant here. So now the CWs are of size this constant. And this is the what you need, the SI to Sn over tau, and these correction, the indicator bits that tell you whether, so these correction vectors are, okay, there are two, right? CW0 and CW1. Yes, but they're both size tau. And you need these correction bits also, right? Well, apply the recursion to these. So now, so this was a not quite working recursion, right? But do a new one. So the CW here will be just size tau. And this will be an instance of recursion going from the dimension t over tau to n. The previous recursion went from n over tau square to n over tau. And what was the overhead? Tau, with the CW. Okay, and that's how you go. So how many of these do you have? Log tau n. That's how many layers of recursion you have. And how much did you pay for each? What's the total bandwidth here? It's the CWs. They dominate. Everything else is locally derived except of the first set of keys, but that can be arbitrarily small. So these CWs are tau times log tau n, which is log n. Okay. Did that convey any information?
Yeah, I'm just wondering why we did the first one then. Is it like harder to use this notation?
Sorry, what?
This so one? We did with no, we did with a square matrix before.
Well, I think that this is oh yeah. So why this? Well, because I mean, look, it's the same idea of squaring that you know that this squaring trick. You know, it's a very general one, right? Just, you know, the first idea is to just, okay, don't think of this as necessarily as a recursion, but just batch them, right? Just batch them into square root chunks of square root size each. And just on this batching, you get an improvement, right? Yeah, maybe you can, in fact, if you envelop this whole recursion, then the whole solution, maybe you don't quite see it coming from this very basic idea.
Okay.
Okay. In fact, the final solution looks very much like it looks the DPF of Gilboa-Yishai. It's very much similar to the GTM, was it? Okay. I don't remember. I think so. PRF. So GTM PRF is a way to go from a PRG to a PRF. the PRF key is a seed. Oh, you know what? Like, we are way over time, right? So if you remember the tree-based PRG to PRF solution, where you take a seed, you take a length doubling PRF, and then you take either the left or the right size, depending on the bit, the first bit of X, of the argument X. And then you take a length doubling PRF, and whether you take a left or a right is depending on the second bit of a PRF. So you have this series of evaluations of PRF, and this value is defined as F seed uses a PRF key at left. So I first went right, then I went left, then I went right, and then I went right. Okay. Okay. DPF of Galois, this recursive solution is that at the beginning you have the two parties have a seed, and they use the PRG to take a seed and create a chunk. So let's just think of this chunk as 2. Okay, so they get 2 values, just like in the basic construction of a PRF from a PRG. And then they apply these corrections such that the resulting values have, so they start with different seeds. So this is S1 and this is S2. And they start from, completely 2 random seeds. But the correction has the property that these are, if the first bit of X at which you evaluate is the same as the first bit of this hidden value I star. Sorry, there is a hidden argument X star on which the 2 PRFs are synchronized. If this bit is the same, then after correction, then let's call it left and left and right for both players. If this bit is the same, if the first okay, I'm getting lost. There's I don't have the okay. So the point is that at the evaluation path that corresponds to X star, the hidden location, these seeds along this path should be different. And along all the other paths, so all the other subtree, right, like the rest of the tree, these are same everywhere except for X equal X star. So you evaluate a PRF like in the basic solution, but you'd have these correction vectors which make the first and the second guy end up with exact, even though they start from a different seed, from same seeds everywhere except along this one path where it gets to X star. And in last layer, the XOR is equal, at position X star equals to Y, of course, right? So the final leaf here, the two leaves must XOR to Y, right? So the final correction vectors is going to somehow encode the Y. All the previous correction vectors just enforce this property that if you stay on the path to X star, the two seeds are different. If you veered from the path, then now the two functions are completely synchronized. So they have the same seed, and from that point on, they will be identical. Yes. So this whole this whole way of taking a seed, running a PRG on it, then looking at then choosing a place, and then applying some correction vector. I mean, the whole thing basically enforces these properties. That if you are at a location that differs from X star, you will end up with the same values, right? So the moment there is some X star path, yes, and you don't know, when you evaluate, you don't know which path corresponds to X star. But the evaluation has the property that once you veer from the X star path, so you are somewhere here or somewhere here, you will end up with the same value. And why? Because it's the basic GGM PRF with the correction vectors that enforce that you will have the same seeds. And therefore, you will do everything the same way. You will apply PRG and use the same correction vectors. Apply PRG and use the same correction vectors. Okay. So this is another way that you can view this construction, right? And if I gave it to you straight away in this form, you would I mean, now I sketched it in a very sketchy way, but you can see it as an instance of the GGM PRF construction with correction vectors at each layer that enforce this property. Okay. Okay. So I'm not sure if that was effective, but we are way over time. So did I lose you, or do you have a question on this?
No, it makes sense. I think it's a good point that they're similar.
All right. Okay. Well, so thanks for watching, and see you next quarter.
See you.